So if you put in inductive loads, so the voltage terminal will be drastically reduced. But if you put in your inductive capacitive load, such as power factor capacitor, power factor correction devices, which the elements are capacitor or capacitive, so you can see that the terminal voltage will rise with load. The more you put in, the higher the rise will be. Then the voltage regulation and phasor diagram. So the means or the purpose of generator part, synchronous generator, is to maintain the voltage and terminal voltage, because when we put in load, for sure the voltage will drop. When you draw more currents, the voltage tend to drop. So we need to keep the terminal voltage constant. So how to correct or rectify this kind of voltage variation? So now the ways that we do is by varying the magnitude of your internal generated voltage. So for example, to increase the terminal voltage is by reducing or decreasing your field value. So when you reduce your field current, resistance. Okay. Let's say if you we draw again the equivalent generation equivalent circuit of the synchronous generator. You can see here V field is on the left side. Meanwhile, your terminal or your armature circuit is on the right side. So this is your RS, this is your JXS. So this is your IF, which flows due to the terminal voltage that you apply to the field. So VF is equal to IF times RF. So if you rearrange your IF to the left, so IF will become VF over RF. So this is the amount or the value of your field current. And so once you reduce your RF, means that you amend your rheostat here, so automatically your IF will increase. So IF will increase. So once your IF increase, means that you are providing more flux or more magnetic intensity, magnetic field intensity to the system. See, when you increase IF, magnetic field will be higher. So the link here will be higher and magnetic fields. So the shaft is rotating. So the shaft rotates in the higher intensity of magnetic fields. So what happens is that your EA will increase. Magnetic fields increase, your phi here increase. So magnetic field, your EA will increase. And when your EA increase, you can see EA is equal to, this is your generated current, IA is equal to IA JXS plus RS and plus VT. And your EA increase, for sure your VT will increase. Your IA increase and your VT also increase. So V phase increase and VT increase. V phase in and VT is the same lah. If you measure at your terminal, for your delta, so V phase and VT will be the same. And if you are having a Y or star connected system, so almost the same lah, but by set 3 of multiply factor. Okay, in another VR equation, other than we just measure the no load voltage at the terminal, some books or some reference they use internal generated voltage at the EA here, and as reference of no load values. So some use EA no load minus V phase at full load, some use and V terminal itself at no load. Okay, all can be used now. Say if the value of voltage regulation operate at unity power factor, the voltage regulation of positive trend will be seen. And if you use inductive load or lagging power factor, or present in lagging power factor, so we can see the positive voltage regulation. So if the value of VR is negative, means that the system operating at leading power factor. So vice versa lah. Negative voltage regulation means that you're operating at leading power factor. And positive, unity power factor. Large positive, lagging power factor. That's what we have discussed previously. Yeah. Okay, voltage regulation and phasor diagram. So internal generated EMF voltage EA here is equal to the amount of V cos theta armature impedance plus, so this is P, this is Q, and P and Q element, real and imaginary parts of the element. Okay, power factor at unity means that the load is resistive. Power factor at lagging means you are operating on the, or you're connected to the inductive load. If you are facing a power factor, leading power factor means the current is leading your voltage, so it means that you are operating on the resistive and capacitive load. So the positivity measured as negative, positive here, and bigger positive here. So here, positive means positive polarity lah, negative means negative polarity. Okay, in terms of power flow diagram, so we shall have a output voltage. So for regulator, for generator, we are measuring electrical output. So your output will be significantly reduced due to the losses of your system due to the stray loss, friction, windage, and core losses, which more to the left side before convert into your output power. After you minus your core loss, copper loss. And copper loss means that your internal resistive of your coil. And the core loss is the mechanical or elimination of your motor or your generator. How you construct your generator materials, so that one contribute to the core loss. Meanwhile, this one is contributed by the selection or the size of your wires which you build the coils. Or you can put in the single diagram here, single line like a fishbone here. So you list down the stray loss, friction and windage, core loss, and here before you P out is your copper loss. And copper loss. So this is your P in. Applied torque times your speed in radian per second. So you shall have your output voltage, output power in terms of cert 3, because this is 3-phase line voltage times your line current cos theta. So power converted from mechanical and electrical. It converted from mechanical to electrical, sorry. So the converted is equal to induced torque times omega m and equal to 3 times of each of your single circuit, EA times IA cos Y here. Y is the angle between EA and IA. So this is what? IA and your EA. And then you can see that your EA is your JX SIA is perpendicular anti-degrees. Okay, this is your armature resistance is ignored in this time. It's ignored due to your impedance here. So your reactance here is much bigger compared to internal resistance of your coil and RA. So the armature resistance is ignored. So you can see that there is no component of RA and RA here. IA, RA here. So only IA and then E. So since IA assumed to be 0, so no electrical loss after your converted power. So we have neglect here. So no copper loss. So P converted is equal to P out. And we assume that P converted is equal to P out. So equal to 3 V phase times EA sine delta over reactance of synchronous reactance value. So from this formula or this equation, you can see that the power of generated system will be maximum when your delta is equal to 90 degree. And 90 degrees sine 90, you get 1. So P max is equal to 3 V phase EA divided by XS. So the maximum power indicated by this equation is so-called static stability limit of generator. This is the highest power that generator can produce. And the induced torque this time is at a certain time is 3 V phase EA sine delta over omega m XS. So omega m in radian per second. So we can see the behavior or the relationship between field current and flux, IF and EA. So this will be the performance in terms of your synchronous generator, IF, EA, XS, RE. So the characteristics above determined with the help of DC test, open circuit test, short circuit characteristic measurement. So what you have done in your lab is to determine this kind of parameters, and what are the reactance, impedance, resistance of the system, the performance, the highest maximum power that the voltage or the voltage maximum voltage the system can produce, the maximum current the current the system can produce. So this one you measure or you done in your lab 5. And so what are the DC tests? So the purpose of DC test is to determine your internal coil resistance. And so what we do is that we put a variable DC source to your terminal voltage. Okay, by right, if you have a generator, so this is your generator. So what you can measure is that you can see your terminal voltage at this point, or the terminal voltage at your terminals or your phase. And so for delta, you will measure the voltage terminal here, same per your voltage at your phase. Meanwhile, for Y connected, you will feel or you will see your terminal voltage, which is set 3 of your phase voltage. Okay, now we are doing the DC test to determine RA. So we take out the this generator, so we don't measure the voltage. Instead, we put in DC source, positive, negative. So positive, negative to the terminal, and the current that flows into your circuit, IDC, is equal to V DC divided by R DC, and R here. So we have to calculate what is the total R that between terminal here, and also we put DC here, and we put DC on this Y connected circuit. So what are the total resistance of RDC here? And so what is the RDC here and what RDC here? So that's what we need to find first. Then we can find your amount of I. Okay, let's say if we are looking at the stator is Y connected. So Y connected, so your RDC will become 2 element of RA, and you say RA plus RA, RA plus RA, and this is your RDC, RA plus RA. So means that RDC equal to 2 RA, and 2 RA. Then your RA will become RDC divided by 2. So this is RDC divided by 2. Meanwhile, if your connection is delta, here delta, so your RDC will become the amount of RA parallel with another 2 RA, and RA parallel with another 2 RA. This is paralleling process, means that RA multiply